In today's lecture, we will cover the Boolean functions, their definitions and their simplifications, and their representation in the form of minterms, maxterms, which are basically the canonical form. So what is a Boolean function? It is a combination of binary variables, binary operators. What are the binary operators? Basic binary operators are or, and the unary operator not, and the parenthesis. For example, here are some functions given here, like f1 is equal to x, y, z prime. It means the value of function f1 is based on the values of variable x, y, and z. The value of f1 will be 1 only if the values of x and y is equal to 1 and the value of z is 0. So there is an AND combination of x, y, and z prime. So f1 will be 1 and 1 only if x and y both are equal to 1 and z is equal to 0. And in this case, when z is equal to 0, z prime will be equal to 1. So next example is that of f2. f2 is the OR combination of x, variable x, and y prime z. It means that the value of f2 is 1 if the value of x is 1 or the value of y is 0 and the value of z is 1. Similarly, we have a third function f3 where which is or combination of three AND terms x prime y prime z plus x prime y z plus x y prime. So the value of f3 is 1 if we have the combinations of x y z in the form of 0 0 1, 0 1 0, 0 1 1, and if the value of x is 1 and y is 0. f3 has three terms x prime y prime z. It means the value of xy should be 0. For f3 to be 1, xy should be equal to 0 and z is 1. Similarly, for x prime y z, the value of x should be 0, y should be 1, and z should be 1. And for the other combination x y prime, the value of z can be 0 or 1, but the value of x should be 1 and y should be equal to 0 for f3 equal to 1. The last function f4 is x y prime plus x prime z. Irrespective of the value of z in first term x y prime, the value of z can be anything 0 or 1, but the value of x should be 1 and y should be equal to 0. Similarly, in the second term, the value of x should be 0 and z should be 1. The value of y can be anything 0 or 1. In this case, the value of f4 will be equal to 1. So we can draw truth table for all of these functions. As you can see, we have used three variables x, y, and z for every function from f1 to f4. So the value we will use three variables x, y, and z in our truth table. The inputs are 3 x, y, z, and there can be 8 combinations from these three inputs. These combinations can be 0 0 0 0 0 1 up to 111. So these are the possible combinations of x, y, and z, and you can see these are the values of function f1, f2, f3, and f4 for each of these combinations. So as can be seen, the value of f1 is 1 only when the value of x, y is equal to 1 and z is equal to 0. Similarly, it is true for all of these functions we have already defined in the previous slide. So first you can write any expression for or you can draw a truth table for a function based on your requirement, and then you can write expression for these functions as well. So as you can see here that the value of f3 and f4 is same, because f4 is basically the simplified form of f3. we have used, we can use the Boolean expressions or theorems to simplify the function f3, and when f3 is simplified, we have the f4 function which has the same output as that of f3. Afterwards, after we write the expressions and we have drawn the truth table, we will use logic gates to implement these functions. So this is the implementation for x plus y prime z. So here you can see that for prime you will use a NOT gate, for plus you will use an OR gate, and for y prime z you will use an AND gate. So basically the input of this AND gate is y prime z, and the input of this OR gate is x plus y prime z. So F3 has basically 3 AND gates. You will use each AND gate for this AND expression, and finally you will use an OR gate with 3 inputs for final output. So for prime you will use a NOT gate. So these are the 3 AND gates for these 3 AND combinations of first one has input x prime y prime z, second AND gate has input x prime y z, and the third AND gate has input x y prime. Finally there is an OR gate for the sum of all these. So this is as you have seen that f4 is simplified version of f3. So when we simplify a function using Boolean algebra, the advantage of simplification is that we have fewer number of gates in our logic diagram. So as you can see now, there are only 2 AND gates and an OR gate with only 2 inputs. So f4 is more economical. So as you have previously done that, you have minimized the Boolean expression to minimum number of literals. A literal can be any variable in primed or unprimed form. So these are some examples for simplifications of functions. As you can see that x into x prime plus y is equal to x into x prime plus xy, where x into x prime is equal to 0. So this reduces into xy only. Similarly, using absorption theorem, you can simplify number 2, and using distributive property and associative, you have simplified it into x. So finally, you will implement these simplified functions using logic gates, because it is more economical to implement these simplified functions as compared to these ones. So here is the complement of a function. Basically in complement you change 0 with 1 and 1 with 0, and you will for any expression you will use De Morgan's theorem to find the complement of the function. For example, a plus b plus c whole prime is equal to a prime. First you will a prime, b prime, c prime. So a function is obtained by interchanging and OR operators and complementing each literal. The few examples to find the complement of any function. Like these one, we have first open the parenthesis. Using De Morgan's law, we have find the complement of these expressions using De Morgan's law. Further, we will use again De Morgan's law to find the complement of this function x plus y prime plus z into x plus y plus z prime. Similarly, this is the complement of f2 . So basically you have to find the dual of the function, you have to complement each literal. But you have to keep this in mind that the plus sign will change into dot sign, and basically you will find the complement of each literal. So this is the dual of this function, and finally you have find the of each iteration. So what are the canonical forms? First we will cover the canonical forms, and in the next lecture inshallah we will cover the standard forms. So in a canonical form, basically we have in the expression we have all the variables which we are using in the function. It means that in each term of the function canonical form we have all the variables. There should be no variable missing in each term. So a canonical form can be in the form of minterms or maxterm. A minterm is basically the AND combination of all literals in their normal form, and basically maxterms is basically the OR combinations of every variable present in the function. For example, two binary variables can have four combinations: x y, x y prime, x prime y, x prime y prime. So each combination is basically the minterm for the function. It is also called a standard product. So n variables can be combined to form 2n minterms, and a function can be represented as sum of minterms or product of maxterms. So a maxterm has basically the OR terms. It is also called a standard sum. Basically, maxterms we have also 2 raised to power n combination, and a maxterm is basically the complement of its corresponding minterm. So suppose we have three variables x, y and z. There can be possibly 8 combinations from x, y and z, and each minterm is basically the AND combination of x, y and z. 0 0 0 is x prime y prime z prime, 0 0 1 is x prime y prime z, 0 1 0 is x prime y z prime, 0 1 1 is x prime y z, 1 0 0 is x y prime z prime. This is x y prime z, and so on. So these are the minterms from m0 to m7. We will use smaller letters for minterms and capital letters for maxterms. So as we have already discussed that a maxterm is basically the complement of its corresponding minterm. So you will take the complement of this function, and it will be equal to x plus y plus z using De Morgan's law, and this is basically the maxterm m0 to m7. Similarly, for x prime y prime z, the complement will be equal to x plus y plus z prime. So these are basically the maxterms, and these are the minterms. So a Boolean function can be expressed by a truth table in this form. There are two functions here, f1 and f2. As you can see, the value of f1 is 1 when the value of x, y and z is 0 0 1, 1 0 0 and 1 1 1. Also the function f2 is 1 when x, y, z has the combination 0 1 1, 1 0 1, 1 1 0 and 1 1. So these functions f1 and f2 can be expressed as sum of minterms or product of maxterms. So in sum of minterms form, we will write for function f1 as it is 1 at 0 0 1. So you will write x prime y prime z plus the value of 1 is 1 at 1 0 0 x y prime z prime, and plus 1 which is xyz. So these are the minterms m1 plus m4 plus m7. Similarly, we can write f2 as sum of minterms. So the f2 is 1 at minterm m3, m5, m6 and m7. So we have written f2 as combinations of m3, m5, m6 and m7. So as you can see that in the previous example of f1, its complement will be equal to sum of minterms. We have written f1 as sum of minterms m1, m4 and m7. So its complement will be the values where its value is equal to 0, which are m0, m2, m3, m5 and m6, and we have written these f1 prime as sum of these minterms where its value is equal to 0. So again, when we take its complement, we have a form of Maxterms product of, when we will take again complement, we have the original function, and we have seen that it is basically the product of Maxterms. So in this way we have proved that any function can be represented as sum of minterms and product of Maxterms. Simply for Maxterms you have to take the complement of the minterms. So these are the basically two canonical forms, or minterms as product of minterms and sum of minterms and product of maxterms. So suppose we have a simplified function and we have to convert it as into sum of minterms form. For example, you have a plus b prime c and you have to convert it into sum of minterms form. So you will see for missing terms. For example, in the second term a is missing, and you will multiply it with a plus a prime, because a plus a prime is equal to 1 and multiplication with 1 has no effect on the term. Similarly, for first term you have seen that b and c both are missing in this term. For at first step you will multiply b plus b prime with a. As you can see, the result is AB plus AB prime using distribution theorem. And again, for each term where C is missing, you will multiply C plus C prime in both of these. Then you will, in the final and in this B prime C term, you will multiply it with A plus A prime. So finally, in the end, you will look for similar terms, and you will discard the similar ones. You will write it only once, and we have this generalized form of all the minterms. As you have seen, there is no variable missing in these terms, and we have written it as sum of minterms form. So this is basically the sum of minterms m1, m4, m5, m6 and m7. You can also write it in the form of summation brackets 1, 4, 5, 6 and 7. Or you can make a truth table for identifying the number of minterms. So also a function can be expressed as a product of maxterms form. So you will use the distributive law to expand. For example, you have x plus yz. You will write x plus y into x plus z, and then you will look for the missing term. Here z is missing, and you will add z plus z into z prime, because z into z prime is equal to 0. Also in this term, the second term x plus z, y into y prime is missing, and you will add y plus y prime. And further you will again expand it using distributive law. You will write x plus y plus z into x plus y plus z prime into x plus z plus y to x plus y plus z prime, and you will cancel out the repeated terms, and finally you have this result. Again, if for example you have to express this as a product of maximum form, so you will write xy plus x prime into xy plus z using distributive law. Again you will use distributive law here, x prime plus x into x prime plus y. Now again one by one you will add the missing terms here, y plus y prime, z plus z prime, etc. And finally you have a collective form of Maxterms, which can also be written as product of Maxterms 0, 2, 4 and